Hello everyone. Thank you for joining. We are really happy and excited to be here with you today. Have you ever wondered what happens after you place your favorite burger order in the Delivery Hero app? How Delivery Hero finds the best rider? How Delivery Hero provides you an accurate ETA? And all of that at millions of orders per day. What is AWS role? Which services are used in this architecture? If you ever wanted to know about that, this is the right talk for you. I'm Victor Valdeviti Pinto, a Senior Technical Account Manager at AWS, and today with me we have Rolando Santamaria Mazó, a Principal Software Engineer at Delivery Hero. Today we'll talk about how AWS powers Delivery Hero's logistics optimization process. In other words, I like to spend Sunday evenings with my family, relaxing, and we usually order a pizza. For that, when you use the Delivery Hero app, we like to get to know our rider, we like to know our ETA, so we have peace of mind to know our pizza is going to be delivered hot and fresh. To do that, we are going to talk about Delivery Hero and the logistics optimization team. Architecture highlights, how AWS Global Infrastructure fits into that, how AWS powers their current architecture, some learnings and best practices. To talk about that, we start with the Delivery Hero and the logistics optimization team.
Thank you, Victor, and thank you everyone for being here today with us. So, it's my pleasure to be here with you to talk about Delivery Hero, logistics, and the optimization processes that take place behind every customer order. We will talk about architectures, AWS, high-throughput, and fault-tolerant systems. Delivery Hero is an amazing company located in Berlin with more than 44,000 employees worldwide. We have an operational presence in more than 70 countries, and we are recognized as the world's leading local delivery platform with own operating marketplace, own delivery, and dark stores businesses. But if you are not familiar with the Delivery Hero logo or never heard about the company, I'm sure that these logos and brands are a bit more familiar to you. Delivery Hero owns all of these companies, and together we form a global delivery network that allow us to reach large population. And you will find, for example, Pedidos Ya delivering in Central and Latin America, or Glovo delivering in Europe and Central Africa. All in all, we are able to reach more than 2 billion people worldwide and to stay as leaders in across multiple segments and geographies. But today's talk is not only about Delivery Hero services for customers or our scale. Today, we are going to talk about infrastructure, architectures, and the complexity behind the optimization process. And why this talk should be exciting for you. The answer can be found in 20 to 30 minutes delivery. I want to ask, is there anyone here familiar with logistics services? Is there anyone involved into up to many days delivery? If you think the complexity associated to many days delivery is way lower compared to near real-time delivery. So, and this is what Delivery Hero has put in place over the years, a set of systems and architectures that needs to be highly reliable, fault tolerant, and be able to deliver near real-time logistics workflows. But Delivery Hero is a logistics powerhouse, and I won't have the chance or the time today to talk about all of the complete platform. Instead, I will focus on an amazing team and an amazing stack that is powering the optimization stack that is at the core of the logistics process. The optimization team have a seat here in Berlin. We are organized across 4 main teams, and our mission is deliver routing infrastructure, so being this connection to the outside world, being able to aggregate all of that telemetry data that is coming out from the outside, and being able to pass it down to our algorithms that are going to do the optimization for the rest of logistics. We have algorithms, we have AI, we have different type of algorithms which are needed depending on the legal constraints or operational modes. We do a lot of experimentation. I have with me one of my responsible colleagues on this today, and we do data analytics and ML and so on. And together we are tasked with the mission of delivering highly reliable, fault-tolerant optimization process for Delivery Hero. What happens if the systems goes down? Well, the pizza that Bito orders will get late or will never arrive, and for sure there will be a big downtime for the whole business. So this team and the architecture that will follow is providing critical services for Delivery Hero, and this takes place in more than 52 countries. To summarize, the following stack is responsible for managing and exposing dispatching infrastructure for Delivery Hero central logistics team. We are responsible for solving BRP and produce dispatching recommendation, basically connecting the order from one side to the riders from the other, and making sure that all of it fits under the promised delivery time and with an efficient cost per order. And we use simulations, historical data, and ML to actually drive forward innovation. Let's start with a few highlights. The following architecture or technology stack is processing millions of orders daily, and we engage over 500,000 riders on peak times. Just to set a little bit the context on the scale. So we optimize our world projection every 1 minute, which means we are constantly moving data across our distributed architecture. I already told you, Delivery Hero is in the near real-time logistics processes. This means our tech stack, it needs to be able to, on every minute, takes the snapshot of the complete world where we are operating and being able to match and provide efficient recommendations to the outside. Information like rider state, order state, sequencing, and a lot of telemetry needs to be accessible every time across the complete distributed chain. And we are getting into architectures now. We adopt asynchronous communication for all of our critical services. This is a little bit aligned to the talk before. And why we do this? Well, because we want to maximize all our reliability, throughput, elasticity, and we want to be fault tolerant. We don't want to be we don't want any pizza to get cold because one of our containers just died, right? So we want systems which are able to recover from failure easily. And here I want to make a pause to explain a bit the different the conceptualization between Delivery Hero service tiers. Tier 1 services, most critical ones, they are directly in the middle of the order processing flow. If one of these services would fail, there's no pizza being arriving. We have Tier 2 services, which are still important, but they have a lower impact. They might die. We might still process in a degraded mode, but you may still receive your package. And then we have Tier 3 and Tier 4, a bit more on the supporting side, right? But there is something very important in our architecture and is part of our reliability manifesto, and that is a Tier 1 service or Tier 2 service needs to stay working even if a lower tier service fails. So that means we have built fallbacks, caching, and recoverability methods in this Tier 1 services, so they can continue working even if a Tier 2 service would die. So another important distinction is our state is recoverable. That means our critical services will manage data sets, as you may get used to it, as you are used to it, right? They are distributed. They are isolated per service, so we follow microservice isolation as per best practices. But we are able to resync in a matter of seconds in case of our state gets degraded. So for example, the state of riders in the dispatching manager can be recovered in the case of a failure. But why is that important? Well, sorry. So why is that important? because this characteristic of our architecture will allow us to make bold decisions when it comes to selecting the database engine behind these estates. And I will get into more details a bit later. So, of course, not everything is recoverable, because we are still a big organization. We manage decent architecture, so we also serve as source of truth for some of the data. For example, fleets configuration or simulations, right? So there is a lot of estate that needs to be managed around the simulation. And that might be scheduling simulation, reports, and so on, queries, analytics, and so on. When we have this need, of course, there is a proper durable database assigned to it, and in the cloud following all backups and recoverability, and so on and so on. We will get into more details later. Finally, in this section, our Tier 1 and Tier 2 services are deployed in a per country basis, so we do isolate resources, and also we deploy them closer to where our users are. In general, we are using 3 regions from AWS. We are deploying in Singapore, we deploy in Ireland, and we deploy in North Virginia in the United States, and you will see that those regions follow strategically where our customers are. And with that, I want to give it back to my colleague Victor to talk a little bit about the fundamentals on the AWS infrastructure.
Awesome. Thanks, Rolando. As you have seen, Delivery Hero has customers spread across the globe, serving different countries at different scales, right? Delivery Hero also needs high throughput, and this is especially split into several different operational countries. All of that is connected to the AWS Global Infrastructure. Everything starts with the AWS region. AWS region is a physical location in a specific place of the world. As you have seen, Delivery Hero uses many different regions, North Virginia, Ireland, and Singapore, and each region has from 3 to 6 different availability zones. Every availability zone has 1 or more discrete and separated data centers. Also, it's important to say that every AWS region is connected via 2 independent and fully redundant transit centers. That creates what we call a AWS Global Network. And why that's important? Everything is designed to have a high availability, high scalability, and high fault tolerance, which is crucial, as we have seen for Delivery Hero, to operate at a global scale. As of today, AWS has 33 different regions and 105 availability zones spread across the globe. When we go a bit more into an availability zone design, it's important to say, as I mentioned before, it consists of 1 or more discrete data centers. And these all have redundant power, networking, and connectivity. I wanted to dig a bit deeper into the distance between the different availability zones within an AWS region. Why this is important? So regions, availability zones, they have to be distant from each other far enough so they don't have a shared fate scenario. What is that? Let's say power disruption, water disruption, fiber isolation, and so on. But they have to be close enough to enable real-time data replication. And that is crucial to many different AWS services, especially the ones used by Delivery Hero, as we're going to see in a few slides. All in all, we are talking about 100 kilometers distance between one availability zone and the other. Different customers, they use different regions and availability zones for different purposes, let's say disaster recovery and so on. But Delivery Hero also uses them to ensure a higher throughput across different countries. So every operational country is served from a different region, and that globally increases the throughput that Delivery Hero can provide for the customers. We also would like to dive a little bit deeper into the AWS service types. So AWS has 3 different service types: zonal services, regional services, and global services. And the difference between them lies in the control plane and the data plane. Before going into that, explaining a bit, control plane is the APIs you use to control the service. So let's say when you create an EC2 instance, this is what we call a control plane API. Data plane is a day-to-day operation of the service. So let's say you insert an item on a DynamoDB table. Why this is important? When we talk about zonal services, the control plane is regional and the data plane is zonal. What that means is when you create an EC2 instance, you're going to be using a regional control plane operation, and you place that EC2 instance in a specific availability zone. And what that means is when you need to scale your application in different EC2 instances, you need to understand if you want to do this within a single availability zone or if you're going to do this across different availability zones. The same for fault tolerance. When there is an event happening in a specific availability zone, how do you make sure you have enough resources to continue to operate your workload at scale? When we go to regional services, both regional and both control plane and data plane are regional. So when Delivery Hero starts to send more and more messages to Amazon SQS will automatically scale within a single availability zone or across different availability zones to accommodate the need for more and more messages. Delivery Hero doesn't have to worry about how this scales because this is a regional data plane operation, right? When we go to the global services, the control plane is a single region and the data plane is global. That means when Delivery Hero, as an example, creates a new entry on the DNS, this is going to be using a single region data plane, control plane API. When it resolves that name, this is going to be done globally. And how is then AWS fully connected to the architecture highlights, as Rolando mentioned before? We wanted to focus here on the zonal and the regional services that Delivery Hero is mostly using. That's the more interesting part for reliability and also scalability. We are going to cover how the services are used and how it's used to scale and be fault tolerant to make sure that my pizza gets delivered and I have peace of mind.
Thank you, Victor. So now let's try to connect what my colleague have mentioned to the concrete services that are in place within the optimization stack or architecture. So first of all, let's talk about the compute layer. We love containers. Who else love containers here? So we talked already, Delivery Hero is in the near real-time logistics processes. So we need elastic compute layer, and we also need fault-tolerant compute layers. So this is what we get when we embrace containers and Kubernetes through the Amazon Elastic Kubernetes service, or EKS. When it comes to the configuration, of course, we have a different set of families just to guarantee maximum availability of EC2 instances. And we have a combination between spot instances and on-demand instances. I have to say, we mostly rely on spot instances, and because we design our systems with fault tolerance in mind, we are not really impacted because spot instance is just leaving the fleet. We know that another one is joining or an on-demand instance is going to be used. If you look at the ratios, we are mostly around 70% spot in a certain time of the day. So to highlight a bit the capacity. So what you see is the capacity that we are requesting. This doesn't mean the capacity we will operate. We scale a lot more because we have auto-scaling configuration in place that is able to accommodate to the traffic. And if you relate to what food delivery related workflows, they are very spiky. So that means, for example, during lunchtime, you will get a huge spike on demand, same as a dinner time, or depending on where everyone's decide to have something for eating together. So looking at the numbers, so this means 1800 cores and more than 4 terabytes of RAM is allocated only for our optimization stack on top of Amazon EKS. And when we need to scale, where this is something Kubernetes take place automatically, so new nodes, new EC2 nodes, or will join the fleet, or we leave it when we don't need it. Within Kubernetes and following AWS reliability guideline here, so we embrace multi-AC deployments. And tier 1 and tier 2 services are deployed with a minimum of 3 instances, and they are spread across availability zones. And as I said, we do use horizontal port auto-scaling in Kubernetes, if you are familiar with it, and we connect that to metrics, so our compute layer will be elastic. Now, let's talk about the messaging layer. I already said our critical systems and our internal integrations happens through messages, asynchronously. And there is no surprise here. So we also rely on Amazon SNS and Amazon SQS as our messaging layer. And this decision allows us to, first of all, operate at a scale, be reliable. We don't have to be concerned on capacity of the queues or an impact on latency. The performance from SQS and SNS is quite predictable. It's still under single milliseconds. And it really provides us a reliable messaging layer. And just to highlight a bit the scale where we are operating here, what you see on this chart refers to one single service, this dispatch service or dispatch manager, the service that gets a lot of telemetry from the outside, do a lot of aggregation, conflict resolution, all of that is related to eventual consistency. You might know about it. And in this service only, we are dealing with peaks of over 200,000 messages per minute. And if you want to see a bit on the global picture, we are again within the optimization stack. We are dealing with peaks of over 450,000 messages per minute, and that is just to understand the scale or what we are operating with SNS and SQS and why we need a reliable layer here. So I already told you we are elastic, and in this on a screen you can see this correlation between the pressure on the message queues and how our compute infrastructure will react to it. And you can see that there is a pattern. So this specific chart relates to our algorithm service, the service that is taking the whole input and is doing the BRP calculation. BRP stands for vehicle routing problem. Is the way in how we connect orders in the one side with riders available in the other side. We do it efficiently and we let it go. We let the pizzas arrive to your home. So, and in this case, we see how the compute resources which are needed are directly related to the pressure on the queues. And all of this is connected asynchronously. So, when it comes to the state, again, we need high throughput, we need low latency. Because our tier 1 services state is recoverable, and we can do very bold decisions in terms of where we put this state, we have decided to go with Amazon ElastiCache for Redis. Because the data pattern fits Redis data structures, and because we can get out of it the best low latency, high throughput possible. And just to highlight a bit on the configuration we are using here. So we are deploying on a per country basis. This is important to mention. We don't have a single Redis cluster that is taking the whole state. No. We do per country isolation. We isolate resources also on infrastructure level. That means also we have multiple ElastiCache clusters running at a certain point on time. And to our surprise, the performance and the delivery, even for the smaller family, so the T4G family, for example, is amazing. So we are able to operate large countries with T4G family between medium and large configurations. And for example, you can see here the CPU utilization is still very decent, allowing us to grow a lot more. So we have 3 nodes, and we have sharding enabled. So in case we want to really grow to more nodes, we have the possibility, but to be honest, so far we are getting enough performance even from this very simple configuration. Important to say about our Redis integration. We do use data structures from Redis, so it's not only limited to key value access. We have pessimistic locking through Lua scripts to maximize throughput. And What else to say? So we use Java, we use Redis on client most of the time because of the maturity. To give you a bit on the dimension on how we are using Redis so far. So we are dealing with handling peaks of 2.6 million get commands per minute on an average latency of around 8 milliseconds. And our payload size is a bit variable, so that's why you see this latency. So we have sometimes kilobytes, but sometimes we have larger payloads as well. When it comes to grading on the databases, we execute 5.5 million set commands with an average latency of 4.2. Again, this is only for the optimization stack. So we also need to deal with we are also source of data for some of our entities. That is the case for fleet management configuration. That is the case for the simulation, as I said. So what we have decided here is to adopt Amazon DynamoDB and Amazon RDS for Postgres. Those engines fit very well with the data pattern or the requirements of the services, and of course we rely on backups and durability features which are provided by AWS around these services. It's important to mention, we try to do our best to avoid anything which is not in memory from being in the middle of the order processing flow. And the reason is because we want to maximize throughput and deliver with the lowest latency. So in terms of these two components or the decision here, so if we need to scale, well, DynamoDB, very scalable, and for RDS as well. So we still have enough room to grow and to increase the size in case we need them. Finally, there is also the need for S3. Who doesn't need S3 these days, right? So our optimization cycle runs every minute. And we want to make sure that we save the snapshot of every one of those optimization cycles. Why? Well, because we have analytics and ML processes that take place afterwards. And we do intelligence, analytics, improvements, innovation on top of this. And picking S3 here comes very handy because, again, we are in the near real-time delivery, logistics execution. So we cannot really waste any second. And with S3, at the end of the dispatching cycle, we get a predictable latency and we are able to save megabytes of data, input and output in S3, and so it can be later on picked by the analytics and ML pipelines. But in today's session, I won't talk about these topics. This is something we can follow up in a different scenario. To summarize, on the screen you will see the high-level architecture for our optimization stack. We have tier 1 services. That means dispatching manager, dispatch service. This is the service getting all the telemetry, coordinating with the outside. We have routes API, the service that aggregates the rider's route, that is serving the rider's route. So if you sign up to be a rider in our app, you will see that you, at any point in time, you need to know where you are, where you need to go next. You have the algorithm engine. This is one of our, let's say, most resource-demanding component. Is the service that is executing the vehicle, solving the VRP, vehicle routing problem. It's a service that is very scalable. That's enough divide and conquer as needed, and growth horizontally to deliver the best optimization every cycle. And like I said, fully on Kubernetes, on containers, and on ElastiCache on this layer. And these tier 1 services communicate through Amazon SNS and SQS. And in the middle layer you have the tier 2 services, fleet configuration. You have also simulation stack and so on. So it's important to mention here, we mostly run on EKS, except one tiny service that is a machine learning model, which is supporting the decision to where to send the order to the customer. It's part of the optimization process, and this one runs on Lambda we never hear about it. It just works. So what else about this architecture? So we are running on the JVM. We use Kotlin. We use Quarkus. Anyone using Quarkus here? Unpopular opinion. We have multiple tiers, as I explained. So all in all, this is our high-level architecture, and it runs, as you see, completely on AWS. So now I want to finalize with a few learnings and best practices. The message that you should take home as part of this session today. As many of you, we also started with monoliths. And while Delivery Hero was small, everything worked. Except when you have to scale, and you have to scale big. Except when you have to prepare for 2x, 3x, 10x growth. And managing monoliths, which are sitting in this particular scenario, is not only hard because of the technology, because of the product. It's also hard because you need to scale your organization. So for us, it became a bottleneck. So you had teams waiting for the other one to release. You had another feature coming. You have a lot of inefficiency, time to market, and so on. So in our case, avoiding monoliths help us at multiple dimensions. Improved organizational productivity, time to market was reduced, but also the ability to scale independently, the ability to deliver more frequently, all of these promises that you might hear when you listen about microservice benefits. And in our case, we can only recommend it. On top of that, you have a lot of services. Do communicate asynchronously. Why? Because that is a communication style that will allow you to be fault tolerant and to have a higher throughput in a simpler way. Of course, you also need to deal with the vendor consistency. You have to deal with data replication, but that is something that in our case, our teams has learned very well, and we do it today at this scale. So, adopt purpose-built databases. This is not only a marketing campaign from cloud providers, it really works. So, database engines are built to support certain access and write patterns efficiently, but there is no one engine fits everything. In our case, as you saw, we are using the database that fits the data pattern. That's why you find Redis in the middle of tier 1 flow, because we need low latency. We need quick movement of state across the multiple services. And also why we selected Postgres for the simulator, because we want richer analytics and query capabilities. Not less important, you are building products for your company. You might not be building infrastructure components, so reuse as much as you can. So we avoid launching anything that is not supported by the cloud provider, because we don't want to be drawn into and putting energy on fixing stuff that is already supported by AWS. And finally, in times where everybody is talking about AI, it's also important to come back to the foundational infrastructure that always work. This is, in our case, a recipe for success at scale. So, and you can say our optimization stack would not be as reliable, as scalable as it is today if there would not be Amazon EKS, SNS, and SQS to connect the components, and ElastiCache to manage our most sensitive and critical data sets. And with that, I give it back to my colleague.
If you have any questions, we are happy to take them. We're gonna be just right outside here, the stage. I hope you learned something new today and you are inspired by the talk. Please give us your rate at the app, and with that, thank you very much.